What's up, everybody? It's Dan from SageMathTutoring.com, and we have some physics problems today for a student of mine who has a test coming up. So let's just dive in. So what do we have here? We have an inclined plane and an initial velocity of 20 meters per second, and I'm assuming this is the coefficient of kinetic friction here. And 30-degree angle, okay, fine. They want to know how far will it travel. So I'm going to assume that this question is how far will it travel up the incline. All right, I'm going to assume that that's what they're really asking. So in other words, what's the distance here until it stops due to the forces acting against it? Then they want to know how long to go up and come back down. So I'm going to assume that what they're really asking there is how long would it take for it to go up and then down again. Now, it is the case that the amount of time it would take to go up is the same as the amount of time that it would take to go down. So that's probably going to be helpful to keep in mind for the future. So we want to know how far is it going to travel up. Well, that's a distance question, and there is a formula that says that the final velocity, okay, this is a formula that my students should be somewhat familiar with. Final velocity squared equals the original velocity squared plus 2 times the acceleration. Now, sometimes they put x here for, horizontal distance or whatever, but I'm literally just going to put a d for distance there, okay? Now, that's a formula that I would recommend for this problem because they are asking for the distance that it's traveling, so already we have that featured. We know the original velocity, it's given right here. It's 20, I'll just say 20, meters per second, but I'll just say 20 here, so that's going to be 20 squared. Plus 2 times the acceleration. Now, we don't know what the acceleration is yet, but we're going to find out, times the distance. We also happen to have the final velocity because the reality is let's say this is shot out of a cannon at 20 meters per second. It is going to go up and everything, but due to, various forces, including the force of gravity, it's going to stop at some point. And in that moment where it stops and then starts to come back down, in that moment where it stops, that is going to be a velocity of 0. So the final velocity is 0, okay? So we can kind of see how this equation is going to work pretty well, but we do need to find the acceleration. So the question is, what is the acceleration? Well, let's take a look. I'm going to draw it again over here, and I'm going to place the box like somewhat up like that. So what we could do is just get clear on the fact that the forces acting against the box, like yes, it's moving at a velocity of 20 meters per second, but there are 2 forces at least acting against the box. One of the forces is this sort of downward pull in that direction, okay? It's this downward pull in that direction because it's, gravity is trying to get it to slide down in that direction. We're going to talk about that in a moment. There's also another force that's working against this box going up, and that would be the force of friction, okay? So we're going to have to take into account both of those things. So we're going to talk about the force of friction relatively soon, but first let's get clear on, well, what is this force that's just bringing it down at an angle like that? And that's where the whole vector decomposition might come into play. So first of all, we know that there is gravity, right? There's gravity acting on this box, which takes it straight down, okay? Now, there's also the fact that the box is pressing into that surface, okay? Now, as my student at home knows, there's what's called the normal force, which is the surface pressing back on the box, okay? So that's happening, okay? That is happening. And then there's also the fact that it's going down in that direction as well. Okay, and this is 90 degrees. So once again, this is due to the weight of the box because gravity is pulling it down, and we know that that's going to be, the mass of the box times g. Now g is 9.8. It is the case that this also this angle right here, I should say, is 30 degrees. That's for sure. My students should know that if that's 30 degrees, then that angle has to be 30 degrees, which means that this vector, this force, could be described as mg times cosine of 30. And this component right here, which is really the one that we're interested in, by the way, is mg sine of 30. So we know that this force right here is the force ultimately that's bringing it down in this direction, down the incline parallel to the surface of the incline. So if we're going to analyze the total sort of net forces acting on this box, we could say the net force, and I'll say X, is equal to definitely the negative mg, okay, negative mg times sine of 30 degrees. Now I'm saying it's negative because it's moving to the left, okay? We're sort of analyzing the fact that it's moving to the left. So that'll be negative mg sine 30. Now we can take into account also friction. Now we're looking at kinetic friction, and we know that this is the mu that they gave us right here. I got to make sure it's in the screen. This is the mu that they gave us, and we also know that the friction in this case, it's going to be kinetic friction. I'll call it F sub k. Well, that's going to be mu times the normal force, right? So I'll just call that Fn. Now we have mu, that is 0.2, right? So then the question is, well, what's the normal force? Well, the normal force, I had already mentioned, is this like yellow force where it's pressing away from the surface of the incline. But that force should be perfectly balanced with this green arrow downward pressing into the incline as well. We already discussed that that's mg cosine of 30. So that mg cosine of 30 can go right here. All right. So that is the friction. Now the friction is, the box got shot out of a cannon, so it's moving up, at a certain velocity, but that friction is resisting it. Okay, so I'll kind of wrap all this in green. We'll color code it. This friction is resisting the box and kind of moving in that direction. Okay, so it's that friction resistance combined with this vector that would be the forces acting upon this box, and therefore the acceleration acting upon this box, which we're going to see soon. All right. Now, the friction is moving, since this green arrow, the friction, the resistance is moving to the left, we're going to call that negative as well. So that's going to be minus 0.2 times mg cosine of 30. Now, it's the case that you can represent this right here as, mass times the acceleration, because that's one of the Newton's laws, that the force is equal to mass times acceleration. So net force is equal to, we can say, total mass of the system. In this case, it's the box times the acceleration. So that's what we have. And then we have gravity, for sure. right? We know that. It's going to be negative m times 9.8. Sine of 30 is 1/2. And then we have minus 0.2 times m times 9.8 times cosine of 30, and cosine of 30 is 0.87. Okay, let's see. And the m's will all cancel, which is what we want. So then finally the acceleration would be a result of calculating this. And if I calculate all this, it becomes, looks like that's negative 6.6, okay, unless I made a careless mistake in the calculation. So we found our acceleration, which was our goal, to figure out how far it goes up, because we're using this formula to find out the distance and we needed the acceleration. So therefore we're looking at 0 equals 400 plus 2 times negative 6.6 times d, and solving for d we would get 30.3. Okay, so once again, unless I made a mistake with the calculation, that's the answer to that. Now, if we're just saying how far did it travel up the incline, well, that's what it would be. If it's how far did it travel just in general, going up and then going down again, of course, that would be 30.3 times 2, okay? Okay, so then they ask, well, how long did it go up and come back down? Okay, so obviously time is playing a role at this point. And, well, I feel like that one is pretty easy, because they're really saying, okay, how long did it take? Probably a couple ways to go about that, but I think probably just this formula should work, where we acknowledge that how long did it go up and come back down. Okay, I think it's probably asking for the total time, but let's just find the total time it took to go up, right? You know, how much time did it take for it to actually go up before it stopped up here? Well, remember, the moment it stopped up there, we're dealing with the final velocity of 0 right there. So we could, you know, put that there. We also know the original velocity was 20. We have the acceleration now, so we're good to go with that. And then we're just kind of trying to find out what that t is. So if we solve for t at that point, it would be 3.03. So that's how long it took to go up. Now, if they're asking how long did it take for it to go up and then down again, we could say total time of the trip. Total time would be 6.06, just multiply it by 2. All right, so that is that one. Okay, so for this one, they want free body diagrams, first of all. So I think probably what the teacher would be looking for there is the fact that there's certainly tension happening here. There's the weight of the box here. So we could say the force of gravity. There's the normal force of this box. There's nothing going this way because there's no friction. And we have tension. Let's see what else. So over here, we have the weight of the box, force due to gravity. We have tension right there. And that's it. That's all that's happening. And the tension definitely equals the tension. Okay, the two tensions equal each other. This weight is different than this one, so maybe I'll label this box A. We can say this is box B, and this is FGA. This is FGB. A. Okay, so let's see. So they want, so that's that. I think that should satisfy the free body diagram part. The acceleration, so the acceleration with the pulley systems, what I would recommend is using the formula that says that the acceleration is equal to, I'm going to call it the driving force. Okay, that's not probably the phrase that the teacher uses, but it's going to be the driving force over the, we can say, total mass of the system. Okay, now I think if you just sort of rely on this formula, it's going to make your life easier when it comes to the pulley type problems. So what is the driving force? Well, the driving force is this guy pressing down. It's the weight of this box. I mean, that's the only thing that's driving the whole movement, right? So that right there is going to be the mass times gravity, right? So that's going to be 2 kilograms times 9.8, which we'll worry about, in a moment. The total mass of the system is just the mass of the two boxes. So we're looking at 2 plus 3. I'll just write that just to kind of demonstrate. Obviously, we're going to have 5 down here, and 2 times 9.8 is 19.6. And if we were to simplify that even further, it would be 3.92. Okay, so that's the acceleration, so we've satisfied that part. Now, maybe it's worth mentioning that the acceleration of this box is the same as the acceleration of that box because they're connected by the rope, right? So now with regards to the tension, I think probably the best way to get the tension is to recognize that the only sort of force being applied in the x direction to this box is T, is the tension, right? So you can use the fact that the force equals mass times acceleration, and we know that the force in this case is T. The mass of the box here is 3, so that's going to be 3, and we already just found the acceleration. The acceleration is 3.92. So that should work, pretty sure. And 3 times, okay, let me just, that's a parentheses. 3 times 3.92 is 11.76. All right. So that should be the tension. Now, the tension, once again, here has to be the same as the tension here. All right, because it's the same rope experiencing the same tension. All right. Let's see. How far does it go from the table's edge? Okay, so there's this dotted line where I guess this thing flies off the table, I guess, because this goes down, it goes and flies off the table. All right, so I guess my first problem is that I'm not sure if they literally mean what's this straight line distance, in which case it would be the hypotenuse of a triangle, which we could find, or whether or not they're asking how far away from the table horizontally it is. That's not exactly clear to me, but either way, in order to get the hypotenuse, I would have to find this horizontal distance anyway. So I'm going to redraw it. This one's weird. This is a crazy problem. Let's see. Here's the table. I'm going to analyze just kind of this part here. Okay. I'm going to analyze just that. And we know that we could kind of imagine this triangle here, a right triangle. And this is certainly 0.8 because that's 0.8. So the question is twofold, really. The question is, what is this? And if they're actually asking for the literal distance from the edge to the spot on the floor, then we would have to find this. So my first sort of thought is, let's find this one first. Now, let's see. This is going down at an acceleration of 3.92. So I guess my question is, if the initial velocity is 0, what's the final velocity once it hits the ground? Because that would, whatever the final velocity here when it hits the ground is, that velocity will remain constant as it goes off the table. So the final velocity when this hits the ground is going to be the same as the original velocity as it leaves the table. That's where my mind is going with it. So I guess the question is, what is the original velocity here? And it seems to me that would be a matter of finding the final velocity when it hits the ground here. Okay, so I'm going to suggest using an equation like this, where final velocity squared equals the original velocity squared plus, I'll just use plus because we're going to be taking the square root. We want this to be positive over here. So it's going to be plus 2 times the acceleration times, we could say, the distance traveled. All right. Now in this case, the distance traveled, it's going down, so it's 0.5. So it's going to be final velocity squared. The original velocity, at least here, is 0. You know, there was a moment in the beginning where it wasn't moving. So that's going to be 0 squared plus 2 times. Now we have the acceleration is 3.92, and we have the distance traveled. You know, it's going to be 0.5. So that is going to be, let's see, the final velocity squared equals 3.92, but then when we take the square root of that, it's going to be 1.98. Okay, so let's see. So that should be right. Now, if that's the final velocity as this thing hits the ground, as I said before, that means that this box will be moving at that velocity as it leaves the table. So that would be the original velocity over here. So I'm just going to call that 1.98. So 1.98, and that's meters per second. Okay, so the question is, how far does this travel before it hits the ground? Well, I'm tempted to use the formula. I mean, really a basic formula, actually. You know, the basic formula is based on this triangle where it's like distance equals velocity times time. And what that means is you could translate that as the distance is equal to the velocity times time, right? So we have the velocity, right? It's 1.98, but I think it's obvious we now need the time, right, in order to know how far it went to the right. Okay. Now, because remember, even though it's going down, we're ignoring that vertical component. We're only focusing on this horizontal component. And that horizontal component, like this velocity remains constant all the way, okay? The only reason it stops is because it hits the ground, right? But that horizontal component remains at a velocity of 1.98. So the question is, how long does it take to hit the ground now? So we now have a separate mission to find out, okay, well, how long does it take to hit the ground? Well, that's going to be a matter of, let's see, probably using this formula. Y equals original velocity times time minus 1/2 times gravity times t squared. Now, y would be that vertical distance, so that's just 0.8. Now this part could be confusing. The original velocity when we're considering this y component is actually 0. And now I know that when it comes to, I should probably just put an x under this, okay? I'm gonna label this as v sub o y because it is true that the original velocity, when you're looking only at the horizontal component, that original velocity is 1.98. Okay, it's definitely going 1.98. It probably started. It hit 1.98 and then it stayed constant from there. But when you only pay attention to the downward action, okay, this downward arrow, this downward vector, the original velocity, before it drops down, from this perspective is 0. It's almost like holding an apple in your hand. So the apple's perfectly still, but then you're just letting it go and it drops straight down, okay? So that's actually 0. So that's going to be 0 times t, which is good. And then we have minus 1/2, and gravity is 9.8, and we have t squared. So let's see. Yeah, sometimes the negatives throw me off. I mean, let's just recognize that this is actually down, right? It's going down 0.8, so we're going to make that negative. Sometimes the signs throw me off a little bit. So we could multiply both sides by, 1/2 right now. That would be 1.6, I guess. And then we have 9.8 times t squared. Okay, so hopefully I'm not making any careless mistakes there. Dividing 1.6 by 9.8 gives us 0.16. And that equals t squared. So then to take the square root of both sides would be 0.4. Okay, so that's 0.4 seconds. So I think we're good to go then, because that's how long it took to go from here and hit the ground. So therefore we could just plug that into this to find out how long it was traveling past the edge in that horizontal direction. So what we're going to do is just replace that t with 0.4, and that should give us that distance, and that is, looks like it's 0.8, and that would be meters in this case. So what we just found is, 0.8 here too, is that this is 0.8. That's what we just found. So I'll replace that with 0.8 right now. Now, once again, if it's the case that the original problem was actually asking how far from the table's edge, if they're really just talking about how far from, like, horizontally from the table's edge, then we've just answered the question. But if it's the case that they actually want this literal distance from the spot on the floor to the table's edge, well, we need to get the hypotenuse. Now, you could always use the Pythagorean Theorem, but this is also an isosceles right triangle. And since it's an isosceles right triangle, this is really going to be 0.8 radical 2. And that is equal to 1.13 meters. So that should do it. There's always probably a strong possibility that the way I did it might differ than the way the teacher would talk about it or what have you. There's going to be some differences there. But I feel as though that is very sound, what I did. So for any of you who have any disputes or questions, just put it in the comments below, all right? But this is sound, as far as I can tell. It's a very complicated problem, right? Very complicated. I feel like this was easy, relatively easy. This was pretty easy, but this one's a whole nother freaking thing, right? So for my student at home, just rewind it as many times as you need to and just watch it. Okay, so we're finding F such that the blocks move at a constant velocity. Well, you know the blocks are moving at a constant velocity when this force, okay, this force is equal to the total kinetic friction of the three boxes. All right, so how can I represent that? We could say F, this will be box 3 because it looks like that's what the teacher wants. This is box 2, this is box 1. So we could say the kinetic friction for box 1 plus the kinetic friction for box 2 plus the kinetic friction for box 3. Now, kinetic friction is mu times the normal force. So, the first kinetic friction would be mu1, because that's given right here. So I'm assuming that's due to the fact that the surfaces under the boxes are a little bit different, I guess. So we have mu1 here times the normal force for box 1, I'll put a little 1 there, plus mu2 times the normal force for box 2, plus mu3 times the normal force for box 3. Okay, so then we have to go on a mission to find these normal forces, which can be really interesting. Kind of feel the need to draw it only with less stuff on it. I do want to keep those angle variables though. So this is alpha right here. We've got a beta right here. And focus on this one first, okay? Actually, we'll focus on all of them, but we're going to zoom into these. So, force of gravity, right? And here's the force that would press into the surface. Now, we know that the normal force is pressing like that, but that normal force is going to equal this force. So what we're really interested in is this vector, okay? Now, I'll extend that. So we're really interested in that. We're interested in the yellow part. And it's the case that this is alpha. Now that yellow part is going to be mg, because this is mg. This is always mg for these incline problems, okay? So this is going to be mg times cosine of alpha. So that's the normal force there. Now, what is m? Well, I guess we're just going to call it m3, okay? So we're going to call that m3 right there. So it's m3 times g, which is, by the way, 9.8, of cosine of alpha. Now, I think we can use the exact same reasoning. Let's just cut to the chase. This is going to be m2 times 9.8 times cosine beta. Okay, now, whatever. I'm not going to find that. I won't cut corners. There's a part of me that doesn't let me cut corners. So this is m2 This is M1G, or M3G. So that's the yellow one there. This one here, it goes straight down. Then we have our yellow guy, which is equal to the normal force. And then it goes like this. This is going to be M1G. And this right here is going to be M1G cosine. This is beta now, right here. Cosine beta. So in other words, it's going to be M1 times 9.8 cosine beta. So those written in black, I'll write this in black too. These are the normal forces for each of the boxes. Can I blow that up? We're going to find out. Can I actually blow that up? Let's see. It's acting crazy. Let's blow it up over here. Can I take it off to the side and blow it up? It's giving me problems. There we go. Okay. See what's happening, everyone? What is even going on? Okay, so awesome. So let me bring it over here. I'll try to bring it over here. There we go. Okay. So therefore, we're looking at mu 1 times something plus mu 2 times something plus mu 3 times something. Well, that's something over here for box 1. Okay, we'll label it box 1, box 2, box 3. That something over here is this M1 9.8 cosine beta. M1 9.8 cosine beta. Similarly, this is M2 9.8 cosine alpha, and this is M3 9.8 cosine alpha as well, because that's over here. So I don't exactly know what the teacher's looking for, but I'd say that that's also sound. There is a case that could be made that because it's somewhat vague and it's so abstract, a case could be made that maybe you could have gotten away with just writing this. But I have a feeling the fact that, again, I said it before, but the fact that the teacher included the beta and the alpha probably means that the teacher wants these values to be included somehow in the answer. So this is a very spelled out version. And also there's the mention of the mu, right? The different mu's, the different masses are mentioned, right? So it just seems a little weird to just throw this at the teacher and be like, okay, I guess I'm done. Moving on to the next question. So you got to actually do all that probably. So that's, it should be true. Now the overarching insight is that if it's a constant velocity, then the kinetic friction has to, the sum total of the kinetic friction has to equal that force. All right. That's the sort of original insight that we're relying upon. Okay, so it looks like we've got 3 more. All right, and let's take a look. So a block of mass, 2 kilograms, pulled by a force of 12 newtons. Calculate the speed of the block after travels. Yeah, I feel like that one's pretty straightforward, actually, right? I suppose we could draw it. We have the block. It's 2 kilograms, and it's pulled 12 newtons, right? What's the speed of the block after it travels 10 meters. Okay. So 10 meters. The original velocity is 0. And we are interested in the final velocity. That's a great picture. You got to give it to me. Right? It's pretty good. So, okay. Well, I'm assuming no friction. There's no mention of friction. And let's see. Well, we know the force is 12, right? We also know that force is equal to mass times acceleration. So I feel like that's enough information to figure out the acceleration, which is probably going to lead to other good stuff. The mass we have, it's 2 kilograms. So 12 equals 2 times the acceleration. So the acceleration is 6 meters per second squared. So what do we have? We have the acceleration. We have distance. We have the original velocity. And we are looking for the final velocity. So immediately, I'm thinking to myself, definitely this one. Definitely this very famous formula. 2 times acceleration. Now, again, I'm used to writing x here, but I'm just going to write d for distance. Yeah, final velocity is the mystery. This original velocity we know is 0. I'll just write that as a way to remind us, everyone, what we're doing. 0 squared. I'll even write squared. So we have 2 times the acceleration, which we know is 6, times d. So it looks like the final velocity squared is equal to 12 d. Oh, but we have d, don't we? Yeah. Well, I don't know why I'm not writing d. D is 10, right? D is 10. I'm not going to tell you what time it is. It's actually pretty late over here. So, I have valid excuses for not writing 10 in that moment. So we have 120. We have v squared equals 120. So clearly the final velocity is the square root of 120, which is approximately 10.96. Okay. So feel pretty good about that one. I feel like that one's pretty straightforward, right? All right, problem number 3. A block is released from rest on a rough incline that makes an angle of 45. Coefficient of static friction is 0.5. Coefficient of kinetic friction is 0.4. Will the block move on the surface? If it moves, calculate its acceleration. Well, you probably know the answer to the first question is yes, right? They're not going to give us that follow-up unless the first answer was yes. So just draw attention to it by putting a circle around it, and we'll go off to the side. Well, we should probably draw it, right? 45 degrees. Cool. I'm going to do it the other way. I'm going to do it like this. We're gonna live on the edge a little bit. I want this block going down in that direction. Okay. Coefficient of static friction is 0.5. Okay. So the mu for static is 0.5. All right. What else do we know? Will the block move on the surface? Okay. Well, what's going on with this block? This block is certainly going down like that due to the weight. There is a normal force here. That's not really the normal force, but it's the normal force is like that. But this is equal to the normal force. And that is something I'm going to talk about soon. And then we have this right here. It is the case that that's 45 in there, 45 degrees. So this normal force situation is 9.8 times m, because that's, mg, times cosine of 45. So, okay. And this is going to be 9.8. The yellow one is going to be 9.8 times the m, the mass, times sine 45. Okay, what else do we know? Let's see. Coefficient of static friction and a coefficient kinetic friction will the block move on the surface. Well, that just depends on if this is greater than the static friction. Like if this force, this yellow force, is stronger than the force associated with static friction, then it is going to move. Okay, it'll break the friction, the static friction. So let's find out the static friction to the best of our abilities. So we're looking at static friction. That's simply going to be mu times the normal force. And actually, in reality, I shouldn't say equals. It's kind of a range, actually, when it comes to not kinetic friction, but static friction. Static friction is a range. This has to be, less than or equal to that, and therefore it's less than or equal to 0.5 times the normal force. But we have the normal force. I'll even keep it color coded. It's this blue force that's 9.8 m cosine 45. So you might be wondering, how the hell are we going to find this out? Because we don't even know what m is. But it all comes down to what I said just recently, that basically if this yellow guy is greater than this number, which is the static friction kind of max force, like once the force reaches this, the block starts to move. Okay, any less than this and the block stays still. But if you hit this force or greater, then the block starts to move. So the question is this vector here, not to be confused with all this yellow. Let me just make this black. Okay. The question is this yellow force here greater than this static friction force? Well, what I'm going to do is just assume it is. I'm going to say, okay, fine. I'm going to say 9.8. Let's assume it is greater. Okay, is that I should say greater than or equal to this force here, 0.5 times 9.8. 0.5, I'll wrap it in parentheses, times 9.8 times mass times cosine 45. Okay, let's keep it in parentheses. Let's just wrap everything in parentheses so we can kind of clearly see what the numbers are. So is that true? That's the question. Now, if it is true, then the block is sliding down the incline. Well, first of all, the 9.8 can cancel. The mass can cancel. And this sine 45, I know is radical 2 over 2. So the question is that greater than 0.5 times cosine of 45. Now cosine of 45 is also radical 2 over 2. So already you can see this is greater because this is half of radical 2 over 2, whereas this is just radical 2 over 2. So this is greater. So it checks out. And as a recap for my student, I have a feeling my student probably gets it, but just in case, we now just confirm that this vector is stronger than the force of static friction. So this breaks the static friction and causes it to move. So, great. Will the block move on the surface? Yes. If it moves, calculate the acceleration. Well, the acceleration, did I mention kinetic friction? Yeah. So they mentioned kinetic friction. That's where that one's going to come in. Let me get rid of this. So, will the block move if it moves? Calculate the acceleration. Well, the net force down the hill is going to equal that yellow 9.8 m sine 45 thing, okay? It's going to equal that vector going down, right? But minus the resistance, the resistance due to friction, and minus, we could say, the kinetic friction. And that will get us closer to finding the acceleration, okay? Clearly, we have to find this kinetic friction thing. And the kinetic friction is equal to mu times the normal force. We already know the normal force is this blue. And the mu this time is the mu, I should really call it mu k. It's the mu associated with kinetic friction. And according to the problem, the mu associated with kinetic friction is 0.4. So, awesome. We're going to have 0.4 times the normal vector, and that normal vector is this blue guy, 9.8 m times cosine 45. 9.8 m times cosine 45. So that's that. I'll bring this over here so it's less annoying looking. Bring it down here actually. So we have f sub x equals, I'll keep it color coded. We're looking at 9.8 m times sine 45 minus 0.4 times 9.8 m times cosine 45. And that's all good. Now, the sort of crucial move you have to make when it comes to, dealing with the net force. The net force going down here, you have to take advantage of Newton's law that says that that's really mass times acceleration. Often they'll put a little x down here. And that equals all this stuff. I'm just going to drop the color coding. I think you get the idea. So we're looking at all that. 9.8 m, that's cosine 45. The masses are going to cancel across the board. So we're about to find the acceleration. Yeah, now that the m's cancel, we actually can just find the acceleration. So this is all just numbers. So if you essentially plug all this into your calculator, you're going to get a sub x equals 4.16, and that would be meters per second squared. That should do it. That should do it. That's how you're going to do that one. For my student at home, once again, feel free to just pause, rewind, put it in slow motion, put it in fast motion, whatever you have to do. But that is the idea there, okay? Quick recap, remember that the static friction is a range, right? Where it's like, friction sub S is less than or equal to mu times the normal force, right? So that's a range, and the kinetic friction is not a range. The kinetic friction in general, like F sub K, remains constant throughout, and we actually found it. This is it right here. Okay, so that's not a range. That's just a single number. So hopefully that makes sense. For my student at home, just remember too, like static friction is you try to push a couch, and at first it's not moving, right? You're pushing, but it's not moving. Well, the force that's keeping it from moving is called static friction. But then once you ramp up the force, once you ramp up your strength enough, at some point it breaks. And then all of a sudden the couch is going to start moving. Now, at that moment where the couch starts moving, that's because you've crossed the static friction threshold. And that's essentially what they're asking here. Is that block going to break that static friction threshold? And it does, right? Now, once the couch is moving, to stick with that analogy, you're still dealing with friction, right? You're still dealing with friction where it's rubbing against the floor, but it's a different kind of friction. It's a new kind of friction, and that new kind of friction we call kinetic friction. And that kinetic friction is just a constant sort of opposing force that's constantly happening, okay? So, problem number 7, we're going to go for the gold right now. Let's see, get rid of that, get rid of that, get rid of that, get rid of that, get rid of all these things. It's probably obnoxious that I don't pause the recording process to do that, and I have to make you watch that. But it's probably much like what happens in school, right? They got to erase the whiteboard, I guess. All right, a block mass M on a rough horizontal surface of coefficient of, okay, this already looks terrible, is pulled with a force of F. That makes it X. Oh my God. All right, so we have to draw this. Pulled with a force of F. Okay. A block of mass. Okay, I see. Right. Okay, so the block is here. It's got a mass of M, but it's being pulled, like by a string, kind of like that, where that's theta. Okay, maybe that's dumb for me to label it that way. I'll label it like this. Draw a free body diagram. Okay, so that's an F as well. So it's like F. Okay, free body diagram. Yeah, I'm not sure the way the teacher likes you to draw that. I mean, you could always just use the XY coordinate plane, personally. Maybe that's completely different, but you could. Here's theta. Here is the force as it pertains to the X component. Here's the force as it pertains to the Y component. There is friction going this way, kinetic friction. So that's kind of resisting the movement of the box. I guess it's accelerating. It's a block, not a box. So it's accelerating. There is the weight of the box, which we could call mg. And then there is also a normal force, which I'll call Fn. The normal force should be less than the weight. it should be the case that this normal force plus this force equals the weight. So I'm going to make that weight a little longer. So for my student at home, just so you understand what I'm talking about, you're used to the box having a weight called mg and a normal force that's equal to the weight. But the way to think about a normal force is that it's the box is pushing down on the ground, or the block is pushing down on the ground, and the ground is pushing back. And that pushing back aspect is called the normal force. Now, because you're pulling up at an angle, you're kind of lifting it at the same time, which means the ground is not pushing back as much anymore, if that makes sense. The ground only pushes back when you push down harder, right? And you know that the ground is pushing back because if you're pushing down harder, well, it's still not moving, right? So in order for there to be that equal and opposite reaction thing, if you're pressing hard down, well, the normal force is going to increase. But if you're lifting it up a little bit, then the normal force is going to decrease, right? Normal force is going to decrease. So the weight stays the same, but the normal force is a little less, because this normal force plus this y component of you pulling it up, these two guys, when you add them, are going to equal the weight. Okay? Because you know that the upward forces in total have to match the weight, otherwise the block would come off the ground, but it's not coming off the ground, right? It's not going up off the ground. So that means that this arrow plus this arrow have to equal this arrow for that to be, an equilibrium situation. What are the horizontal and vertical components of F? Well, by the way, for my student at home, with the free body diagram, just be really clear on exactly what your teacher wants to see here, okay? I kind of busted out an XY coordinate plane. Maybe I should have drawn all the arrows and everything on this thing. So I'm going to leave that up to my student. Just make sure you definitely mention the weight, you definitely mention the friction, definitely mention the force pressing, the angular force. You got to put your theta in there, and then decompose this vector here, okay? That's what I would do. So, but that could be also up to the teacher exactly how they like to do that. So, horizontal, vertical components. Well, this is equal to F times sine theta, okay? And this is equal to F times cosine theta. F being this hypotenuse. So I think we satisfied that one. Contact force, I'm going to assume they're talking about the normal force there. How much is the ground pushing back? Which is a reflection of how much the block is pushing down. So maybe when they say contact force, they mean the force of the block pushing down on the ground, even though you're kind of lifting it a little bit. The block is still pushing down a little bit. Whatever that pushing down is, that's going to be equal to this new normal force, because the block is still pushing down a little bit, and the ground is still pushing back a little bit, and it's pushing back F sub n. So my previous sort of insight or whatever applies, where I had already told you that this weight of the box is going to equal this vector plus this vector when you add them together. So the weight, which is mg, is going to be equal to the sum of F sub n, which really is the contact force, I'm assuming, plus F sub y, and if we solve for the contact force, it would be mg minus F sub y, and the mass is m, so that's fine, so we can call that 9.8 m. Minus F sub y, now we already mentioned that F sub y is F sine theta. I think that's fine. I think that's enough. Let's see, the acceleration of the block. Acceleration of the block. Well, it's definitely moving this way. And that makes me think we have to deal with the sort of net force in the x direction kind of thing. So that's going to be this arrow minus that. So that's going to be F cosine of theta minus F sub k, and let's see, F cosine of theta minus mu k times the normal force. And the normal force we already talked about, it's that. So it's kind of getting messy. I'm not really sure if this is what the teacher is looking for. But this is all true, though. So just to be clear, F sub k is the force of friction. And there it is. I don't know if I need to distribute. I'm not sure if the teacher cares about you distributing. You'd be distributing a negative mu into both of these. Because it's mu k times the normal, we already figured out what the normal force is. Now, the acceleration, though, is a matter of recognizing that this is mass times acceleration. And we are certainly looking at acceleration equals all of that stuff, minus mu sub k times 9.8 m minus F times sine theta over m. So that is true, but there's always a question of, is that exactly how your teacher wants you to answer these? There's sort of a lingering question about how much should you simplify that. And there might be other sort of small differences. Certainly there could be some variety between how I did the free body and how the teacher does the free body diagram. But whatever the process is here, it would be something along these lines for sure. So that's that. Also, I'd be curious if the teacher needs this vector decomposition in the free body diagram. In fact, you might not need the vector decomposition, so perhaps what the teacher wants for the free body, so I'm sorry to go back and forth like this, but it's possible what the teacher wants is maybe something like this. F, right? Mg. Fk. And then there's the normal force, Fn. It's possible that's all the teacher wants there. I kind of added in these components. But that's the next question. Part B, they asked for the horizontal and vertical components. So that could have been the time to bring those in. So it's possible that this is what the teacher is looking for there. So I'm going to make it a little heavier though, because otherwise it's kind of obvious that it's going off the ground. It's probably something along those lines actually. So anyway, for my student at home, hopefully this is helpful. Hopefully it was clear. Hopefully it matches sufficiently the way that your teacher's going about things. It's kind of after my first physics session with this student. We've done math prior to this, but I still have yet to be very familiar with the style of the teacher. Sometimes you can get that information from looking at their notes and seeing, what kinds of, even like whether or not you need to mention the units at the end, if you're given the acceleration, do you really need to say meters per second squared, etc. So I'm going to kind of, for my student at home, I'm going to leave it up to you to just know those like details and stuff. I would definitely review this one with your teacher. Just get clear on exactly how your teacher wants this one to be answered. Everything I did is sound, but that doesn't necessarily mean that it's exactly what the teacher wants. As far as the rest of these, though, this one was straightforward. That one was straightforward. Say that's very straightforward too. Let's see. The one about the very abstract one with the alpha angle, the beta angle, because it's abstract, like this one, meaning it's just chock full of abstract values with no actual numbers, that could lend itself to a lot of stylistic stuff when it comes to the way your teacher wants you to talk about things. So I would double check on that one for sure. But yeah, all the other ones that feature actual numerical quantities are more straightforward and less sort of debatable with regards to how to go about those. But anyway, for my student at home, good luck, a bit of a crash course, and I hope this helps, and I will talk to everybody soon. Take care.